Welcome to Excel 2010 Statistics video number 79. Hey, if you want to download this workbook, Business 210 Chapter 9 second. We already had one workbook for the last video. This is the second one. Or you want to download the PDFs, click on the link below the video. Now here's our second example of a hypothesis test. And I just want to remind you that over in the PDFs on page 30, 31, 32, 33, there's some great notes on Excel functions and the different types of hypothesis tests and stuff like that. All right, last video we did hypothesis testing. We knew sigma, population standard deviation, and we did a one-tailed test to the right. This one we're going to know sigma, and it's going to be a one-tailed test to the left. Here's our example. A bottle of yummy red ketchup is labeled as having 16 ounces of ketchup. A consumer group in the Green Valley area believes that the bottles are filled with less than 16 ounces and asks a government agency to investigate the underfilling. At the 0.05 significance level, can the government agency conclude that the bottle is being underfilled in the Green Valley? That's what you get for writing your own stuff. Green River is a community college just down the street from the community college I teach at. So Green Valley error. From the company data, we estimate the population standard deviation is 0.05. All right, now the first thing is we want to figure out whose point of view this is. In this example here of ketchup, a bottle, a product that's filled, we're going to do it from, in this example, the consumer point of view. Next example, we'll do it from the manufacturer point of view, and you'll see that the way you set up the hypothesis test is slightly different. All right, so the point of view. Well, we have a consumer group and a government agency, and they're concerned about underfilling and label accuracy. We are considering the population of ketchup bottles in the Green Valley area. And our goal is to run a test, run a hypothesis test to provide statistical evidence to support the claim that the bottles are being underfilled. Or that's the way we're going to set up the test to support whatever our conclusion is. Now, this example here, someone thinks that the bottles are being underfilled. So the way you think of this is the mu from our population in Green Valley is less than the hypothesized mu of 16 ounces. Now 16 ounces comes from the label, right? So you assume that that's true for the test. But in order to set this test up, you got to think, okay, less than 16 ounces. Notice the less than symbol would be pointing this way. So that would make it a one-tailed test to the left. Now as soon as you do that, for some people it's easier just to look at a picture, right? There's a picture. So something we're going to be testing on the low end. But what you do to set up the official hypothesis in step one, the null hypothesis, the original claim, and the alternative hypothesis, is take, as we saw in last video, you put h sub 0 colon mu, h sub a colon mu. We have our comparative operators and then our numbers. Now our numbers are going to come from the label. So 16 ounces. I'm going to come down to step 3. Our hypothesized mean is going to be 16 ounces. I'm just going to put that right in here. I'm going to lock it with F4, Control Enter. Notice I highlighted both cells. Control Enter puts the formula into both cells. All right. I'm going to put ounces. Notice I'm going to highlight both cells and Control Enter. It puts the thing into both cells. Now, just as in last video we saw, the trick is you set everything up, and then the only hard part is figuring out the comparative operators. Well, no problem. We already know this is less than, so we're going to go to the alternative first, space less than symbol. Now I'm going to come up here. Once you get the comparative operator for the alternative hypothesis, you flip it and add an equal sign. Space less than, greater than, equal sign. The null hypothesis always gets the equal sign. All right, and notice that comparative operator is pointing that way, so that means it'll be a one-tailed test in that direction. We have alpha. That's the risk of rejecting our null hypothesis when it's true, 0.05. Now we can come down here. sigma standard deviation of the population is known, so we'll put 0.5. These are both in ounces. We don't know that, so I'm going to put NA. A couple of videos ahead, we'll definitely see how to use the t-distribution for sampling distribution, because most of the time you don't have sigma. The test statistic to be used. Well, we know sigma, so that means it's z. Sample size, I'm going to calculate my sample over, I have my data. I've government agency in the consumer group or whoever did this test went out in the Green Valley area and randomly selected different bottles of ketchup from different retailers. So we have the sample data. Those are numbers, so I'm going to use the count function. Control-Shift-Down arrow. Wow, that's a lot. I'm going to hit the F4 key. Now, I don't really need to lock those with the dollar signs, but that jumps the screen back up. All right, now I'm going to do X bar. That's average. We know it calculates the mean. Control-Shift-Down arrow, F4. All right, so we have 15.958. Now, just for kicks, sometimes it's easier to deal with a certain number of decimals. I'm going to round this, comma 2. So round some number, whatever it is, a number, a formula, a function. We have average. I'm going to select 2 because I want it to round to the second digit. Here, you can see over here, there's the decimal, and you count 1, 2. So that's the position I want to round to, and that is a 2. So I get 15.96. So our sample shows a little bit of underfilling. Now our alpha, I have that up here. The type of test, this is a one-tail to the left. All right, now we got to calculate our standard error. We know for the sampling distribution of X bars, the variation is less than in the population, so we calculate our standard error. We know sigma, so we take that divided by the square root of our sample size. So there it is, 100. Now we can calculate our test statistic. And our test, let's look at this picture though. I'm going to right-click that cell, show, scroll over. All right, so here's our picture. We have one tail to the left. Our alpha determines the hurdle, and we'll determine that actual critical value point in just a moment. Anything to the left, we're going to reject our null hypothesis, except the alternative, which, yes, it is underfilling. Anything to the right of this line, we fail to reject H sub 0. Now, for the underfilling, we have this point, right? We take a sample. We need to determine whether the difference between this particular X bar and our hypothesized population mu 16 ounces. Is that difference statistically significant, or is it statistically insignificant? Everything this direction is statistically insignificant. Everything this direction is statistically significant. All right, so that's step 3. Now let's go ahead and calculate our z. Remember the z, this distribution is z. We have in our 0 point z, where that's where 16 equals 16, so there is no difference. But z, our test statistics, tells us how many standard deviations above and below, so let's do it. Equals, we take our x bar minus our hypothesized mu divided by our standard error. We just calculate. All right, so minus 0.8. So it's somewhere along there, right? Minus 0.8. Now what we need to do is calculate our p-value. We have 2 methods of determining whether this number of standard deviations is statistically significant or not. P-value, when we calculate our p-value, we will compare it directly to alpha. Here's our rule. If p-value is less than or equal to alpha, reject the null hypothesis, accept the alternative. Otherwise, fail to reject. So let's calculate our p-value. NORM.S. DIST goes from z to probability. inverse goes from probability to z. So I'm going to select dist. It wants a z. And then comma 1. Now, remember, these normal distributions, it calculates from negative infinity all the way up to your z. So when I enter, wow, 0.21. So that's huge compared to our alpha. Now let's go ahead and I'm going to right click here and show this one. So this is step 4, where we actually go ahead and calculate. So here's our alpha. That's our hurdle. When you're using the p-value, alpha has a probability. It's 0.5. That's our risk. But when our p-value, our calculated p-value, because our z-test statistic is 0 minus 0.8, all that probability says the probability of getting minus 0.8 or less. So our probability, our area here is much bigger than alpha, so we know we're going to fail to reject. The second way to do this is to calculate our critical value. That's that point, critical value, and compare it directly to our test statistic. Equals NORM.S. Inverse gives us probability from probability to a z. So I'm going to take this probability of alpha. Remember, alpha determines the hurdle, and that's what we want right now. We want the hurdle. These two methods always lead to the same conclusion. So now we compare. And it's all about, is it over the hurdle, right? 0.8 is not over the hurdle, right? So we compare these two, and we come to the same conclusion, fail to reject. Move this up a little bit here. And then we always very carefully write our conclusions. Because our p-value of 0.21 is bigger than our alpha of 0.05, we fail to reject h sub 0. Notice we don't say it's true. Our test isn't going to prove that. We've controlled for alpha but not for beta. So using our critical value, because our test statistic of minus 0.8 is bigger than our critical value of minus 1.645, we fail to reject. Probably we want to say more than either one of those. That's kind of the basics. The sample evidence suggests that the mean amount of ketchup in the yummy red ketchup bottles is not less than 16 ounces. Another way to say this, at alpha of 0.05, the sample mean of 15.96 ounces does not provide statistically significant evidence to suggest that the bottles are being underfilled in the Green Valley area. And finally, we'll mention beta risk, because in our last video, we actually had statistical evidence to reject the null hypothesis. Here we don't, so we run the risk of a beta error. Our beta risk type 2 error, that is, we do run the risk of failing to accept the alternative underfilling when h sub 0 was false. In essence, not accepting the alternative when in fact it was true. All right, that's our second example for hypothesis testing. Sigma known, and we did a 1 tail on the left. When we come back, we'll do sigma known 2 tail. All right, see you next video.